Okay, good morning everyone. So today we are going to tackle the Z scheme. Okay, we're going to need lots of energy, lots of enthusiasm to tackle this, so I would think it's adequate that we listen to a little piece of music to put you in the mood. Okay, so that should boost your energy, and here we go. So our aim today is to understand the Z scheme. So we're going to do lots of things today, but the final aim is for you to understand how the Z scheme works. To do so, I would advise you to take an extra sheet of paper and write some of the equations, concepts, vocabulary we're going to use so that you know what we're talking about. Okay, here we go. So we're just going to explain a few things to start off with. So this is what the Z scheme looks like, and we are going to just state the things you already know. And to do so, I'm just going to take my pen tool device. Here we go. Okay, so on this diagram there are some molecules you know. So obviously water and oxygen. You know that water loses electrons, so we've got the electrons here that have been lost by water. You also know that NADP is an electron acceptor and will become NADPH2. We've talked about NADP and NADPH2. This is another way of writing it. I'm not going to go into the detail, but it can be written in this way. So what we know is that the electrons are going to go through different proteins and photosystems. So you know photosystem 2, photosystem 1, and all these CoE, Theo, Q, PQ, CYB6, F, PC, A, FD, FNR. These are proteins which will help transfer electrons. Last thing maybe we can add is that we've got light coming in, so this is to symbolize that light comes into the system. So obviously we'll explain a bit more of this later on, but the key things is that the Z scheme will help transfer electrons from water all the way to NADP, and we'll see how and why this Z scheme is here to do that. Okay. So we'll do quite a few recaps to understand this, and the first one we're going to do is the following. To put photosynthesis into a nutshell, we've already said this, it can be two reactions. An oxidation of water and a reduction of carbon dioxide. If life were easy, this would be the end of the lesson. We could simply say, okay, photosynthesis is these two reactions, and instead of having 40 pages to the booklet, there would only be 10. But life being complex, the coupling of these two reactions can't be done directly. There are intermediate steps which will allow the coupling of the oxidation of water with the reduction of carbon dioxide, but it can't be done directly. And I actually think there is a plot that's been organized by natural selection and plants. I'm sure they've plotted this so that poor S7s and poor teachers need to spend lots of energy to explain this. But having said that, it is also quite interesting and quite fascinating how all of this works. So let's see how this works. So just a brief recap, we've already done the global equation of photosynthesis. So if you add up these two smaller equations, you end up with this one, and if you balance it, that's the global equation of photosynthesis. What I didn't insist on is how the electrons are exchanged, and that's what we're going to do today. So what you need to understand is that the electrons that we have here, they've been taken away from water and they are going to be given to CO2. So these electrons here, it's a transfer from water to CO2. We're going to do lots of recaps which concern physics and chemistry, and especially when we're going to deal with these oxidation and reduction equations. First thing I'm going to give you is a way to remember the fact that oxidation is a loss of electrons and that reduction is a gain of electrons. And the way to remember this is the following picture. An oil rig. You may wonder why. Well, it's simply that if you decompose the letters, you can end up with, so oil, oxidation is loss of electrons, and rig, reduction, is gain of electrons. This is a way of remembering it. Okay, so some vocabulary about this. So a redox reaction, and this is the general way to write it, is that one molecule, an X molecule, is going to transfer electrons to an X molecule. So what does this imply? X is oxidized by Y. Basically Y is taking the electrons away. That's why we say that X loses electrons. And we say that X is a reducing agent. Why is this said? Because the Y molecule will be reduced because of the action of the X molecule. Let's do the same thing for the Y molecule. As Y is going to gain electrons, we'll say that Y is reduced by X because it's thanks to the action of X. So Y gains electrons, and it is said that Y is an oxidizing agent because it's a molecule which can oxidize another one, and in this case Y will oxidize X, therefore taking its electrons away from X. So this is a bit theoretical and general, so what we're going to do immediately is transfer this knowledge onto the example we're going to deal with. So in this case, the X molecule could be two molecules of water, and the Y molecule would be CO2. So there's a transfer of electrons from water to CO2. Okay. In the process, water is going to be called a reductant or a reducing agent, and CO2 is going to be called a oxidant or an oxidizing agent. So this is the general thing. Water is going to transfer electrons towards CO2. So what we can do now is balance this and to explain what's happening in plants. Okay, so let's have this little story. Once upon a time, water was walking along and it encountered CO2. So water said, "Hello CO2, would you be interested in electrons? Because I like giving electrons." And CO2 said yes. CO2 said, "I love gaining electrons." So the went to transfer. So water was happy to give electrons and protons to CO2, and CO2 was happy to gain these electrons. In the process, the water becomes dioxygen and the CO2 becomes CH2O plus H2O. So this is the first thing. Water gives electrons to CO2. However, we've said that in plants it's more complex. You can't directly couple these two reactions, so water can't directly give its electrons to CO2. The story is a little bit more complex, so next slide is going to be a first level of detail. Okay, so as I said, these two equations can't be directly coupled together. There needs to be an intermediate, and this intermediate, you already know it, it's NADP. Indeed, we're going to have water, NADP, and CO2. These are free molecules. So there we are. Okay, so let's have a little play and explain this story. Once upon a time, there were 12 molecules of water, and these molecules of water like to give away their electrons. Obviously, this is set in a chloroplast. In this same chloroplast, we have CO2 which comes along, and CO2 was saying, "Oh, hello, I like to gain electrons. Would anyone have electrons?" And in the crowd, there was a cunning molecule, NADP. And NADP thought to itself, maybe I can take the electrons from water and transfer them to CO2. So this is how it went. NADP came along and said, "Water, do you have electrons I could give to CO2? And the water said, well, my good friend, obviously I do. Here, have some electrons. Okay, I'll give it to CO2 then." And this is what happened. So water gave 24 protons and 20 electrons to NADP. In the process, water became dioxygen, and NADP was reduced to NADPH2. The story has it said, "Oh no, I've become NADPH2." And then NADPH2 said, "Oi, CO2, do you want some electrons?" And CO2 said, "Well, yes, my good friend, I love receiving electrons." And in the process, NADPH2 became NADP, and CO2 became glucose and 6H2O. So to recap all of this, some molecules will naturally give electrons away. This is the case of water. Some molecules will gain electrons. This is the case of NADP. NADPH will naturally give electrons away, and CO2 will naturally take electrons. So this is a more detailed view now, is that electrons are transferred from water to NADP. NADP becomes NADPH2, and NADPH2 transfers its electrons to CO2. This is a first level where NADP is an intermediate. We'll see later on that there are other intermediates, but this is to give you a first idea of what's happening. You may ask, why on earth does NADP talks with a bad impersonation of a Cockney accent? I do not know. That's what I read in scientific research. Okay, so that was the story of how electrons are transferred from water to NADP, to NADPH2, and to CO2. I've just realised that I've forgotten a 6 CO2, so I'm just going to add it. So 6 CO2, so that it's balanced. Okay, so this for the moment is fairly straightforward. So what we're going to do now, we're going to detail this first step. So how on earth does water transfer electrons to NADPH2? So we're going to look at the first step, and this first step intervenes within this Z scheme. Okay, so again, this for the moment seems fairly straightforward. Water loses electrons and NADP will gain electrons, but we'll see that there is a little twist to this, and we'll see why. So, just to recap a few things, you know that protons are needed to produce ATP, so we saw this, protons go through the ATPase complex and that helps produce ATP. Number 2, electrons are needed to reduce NADPH2. So NADP plus 2 electrons plus 2 protons will give NADPH2. So that's things we already know. The 2 questions we can have now is, the first one, how does photolysis occur? So how does the splitting of water occur? There's one question we'll have to answer. We'll see that light doesn't directly hit the molecule, if I may speak so. It's a bit more complex than that. And second question, how are the electrons transferred from water to NADPH? So how do the electrons go from water to NADP? So it would be more correct actually to say to NADP and will become NADPH2. Okay, so that's the second question. So just for it to be clear, how are electrons transferred from water to NADP, and in the process NADP will become NADPH2. Okay, moving on. So it seems that we've got a nice and simple coupling. We've got our 2 equations. If we balance them, 2 molecules of water will give 1 molecule of dioxygen, 4 electrons, 4 protons, and other equation, 2 NADP plus 4 electrons plus 4 protons will give 2 NADPH2. So here we are, and we end up, I realised I forgot the 2's here, so I'm just going to add them. Sorry about that. So we should normally end up with the following equation. 2 molecules of water plus 2 NADP gives dioxygen plus 2 NADPH2. This seems fairly forward, but there is a problem, and the problem is, so this reaction, again I forgot to add the 2 here, the problem is this reaction is not chemically possible. It is impossible for the reaction to occur spontaneously, and this is a problem because it seems to be the case in plants. So how do plants tackle this problem? We'll see that later on, and the first thing we're going to explain why this equation is not possible. So the answer to this is something called reduction potential. So what is reduction potential, you may ask? So we're going to detail this. So again, you might want to take a few notes here. So reduction potential can also be called reduction potential or oxidation reduction potential, and it measures the tendency of a chemical species to acquire electrons and thereby be reduced. So it's the capacity of a molecule to take electrons. It's measured in volts or millivolts, so it's quite logic because we're measuring the flux of electrons and how electrons are carried from a molecule to another. And the last thing we can say is that each molecule, each chemical species, will have its own reduction potential. So this is interesting. The greater the species affinity for electrons, the more positive the potential. So these potentials, they are measured with probes, and physicists and chemists, they've got grids and tables where they've got all the reduction potential measurements. The key thing we need to know for our biology lesson is that the more positive the potential, the greater the species will take electrons, will have an affinity for electrons. Okay, so I'll let you maybe write this down and have a think about the words and make sure you understand this reduction potential. So there's a capacity of being able to take electrons, and each molecule will have a different reduction potential, meaning some molecules will be more capable of taking electrons and some molecules will be less capable of taking electrons. Okay, I said earlier on that physicists and chemists can know what the reduction potentials are for different molecules. So here is a table. You can see that the reduction potential value is here. The symbol is E0 and it's in volts. Protons are highlighted because physicists have established that the potential for protons is 0, and therefore all the other potentials are compared with protons, and this gives you a scale of the reduction potential for the different molecules. So for example, this molecule here, F2, this has a high reduction potential. This means that this molecule is really capable of taking electrons. On the other side of the grid, for example, Na plus has quite a low reduction potential, so this molecule will have a lesser capacity to take electrons than F2. And you've got all the other molecules which are in between. So the higher, so when we go towards these numbers, these molecules have a bigger capacity to take electrons. These molecules have a less capacity to take electrons. Last thing, we can talk of something called a redox couple. So for example, F2 and F minus, they are a redox couple. Another example could be Fa3 plus and Fe2 plus, they are another redox couple. So here's the definition. A redox couple is an oxidizing species and its corresponding reducing form. So when you've got the two, the oxidizing species and reducing form, this forms a couple. So again, we can take another example. CaCu2 plus and Cu, the two together, they form what is called a redox couple. Okay. So, why are we doing all this? Because we want to explain why the reaction which seems to occur in plants is not possible. So, for the first half equation, so this one here, so the couple water and dioxygen, their reduction potential is 0.8. Okay, so for the couple H2O, water and oxygen, their reduction potential is 0.8. Whereas NADP, NADPH2, their reduction potential is minus 0.4. So what does this mean? This means that this first couple has a bigger affinity for electrons. That means that this couple is more capable of taking electrons than the second couple. So NADP and couple has a lesser affinity for electrons. They are less capable of taking electrons. So you don't need to know this, but it's just to explain how physicists have explained this. To know where electrons go to, we've got this basic rule in physics. If you've got the reduction potential on a line here, so the higher potentials to the top, reactions can only occur this following way. So we're going to do an example with our molecules. So let's have our redox potential axis. So our first couple is NADP, NADPH2. They have a lower redox potential, and our second couple is O2, H2O, and their redox potential is 0.8. You can see I've kept the same colours. So O2 is the oxidant. That means it's capable of taking electrons away from another molecule. H2O is the reductant. It's capable of giving electrons. NADP is the oxidant for couple 1. It is capable of taking electrons. And NADPH2 is the reductant of couple 1, and it's capable of giving electrons away. So as these couples have a certain redox potential, when we place them on this redox potential axis, we know that the reaction can only occur in a certain way, and we're going to use what physicists do, this arrow. So just a recap: the more positive the potential, the greater species affinity for electrons. So this means that dioxygen has a bigger capacity of taking electrons than NADP. So therefore it's dioxygen which will take the electrons. So the electrons, they go towards the couple with the high redox potential, so electrons will go to O2 rather than going to NADP. Okay, so this is how physicists do it quickly. We've got this, I call it the redox roller coaster. Whee! And you know that when you've got this, O2 plus NADPH2 will give NADP plus H2O. I haven't balanced this, it's just to give you an idea of which ones are the reactants, which one are the products. Okay, so this is a lot of information, but what you can remember from this is that according to chemical and physical rules, because of redox potentials, the equation that can naturally occur is O2 plus NADPH2 will give NADP plus H2O. But the problem is, and that's what we're going to see in the next slide, so this reaction, this is a balanced version. This reaction occurs spontaneously. Well, that's the problem. In plants, it's the opposite reaction that occurs. So in the thylakoids, we have the opposite. We have water and NADP, which will give O2 plus 2 NADPH2. So this is the main aim of the Z scheme, is that the Z scheme will make this reaction possible when normally it shouldn't. As I said, this reaction here is spontaneously possible, this one isn't. We'll see that the Z scheme is going to allow this reaction here to become possible. So let's have a look into that. Okay, so you probably recognize the axis of the Z scheme. So what we have here, E0 is the redox potential. So these are lower redox potentials and these are higher redox potentials. So do you remember what we said? The rule is the following: electrons go towards the couple with the higher redox potential. In other words, a transfer of electrons will spontaneously occur from a redox couple with a lower RP to a redox couple with a higher RP. Sorry. So in this case, following the laws of physics and chemistry, electrons can only be transferred, so from a lower to a higher redox potential, so for example here minus 0.5 to 0.8. So normally electrons should go from NADP to the water dioxygen couple. However, in plants it's the opposite. So plants have had to find a way to bring the electrons all the way up to NADP plus, NADP, and this normally shouldn't happen, and this is where the Z scheme will intervene. In this part here, so to do the opposite reaction, so this one is not happening where normally it should be, but it's not. So the reaction which will happen is going from water to NADP, which normally is not possible, so we'll see how. And I've circled out this area because the Z scheme will allow electrons to go from water all the way up to NADP, which normally shouldn't be possible, and the Z scheme will make this possible. Okay, I'm just going to do a last recap because this is really important. So as I said, normally electrons should go from NADP to water. This is what normally should happen, but this doesn't happen in plants. In plants we have something else. We have the opposite reaction, which normally shouldn't occur, but thanks to the Z scheme which will be placed here, this transfer of electrons from water to NADP will become possible because of the Z scheme. So the Z scheme will make this transfer of electrons from water to NADP, it will make it possible. Okay. So here we are. So this transfer of electrons from water to NADP will imply that we need all of this Z scheme, so all these protons, all these photosystems, to bring the electrons from water to NADP, and normally this should not be possible, but thanks to the Z scheme it is. Okay, so I am aware that this is quite a complex part, so I would advise you to perhaps review some parts of the video, make sure you understand step by step. If you have any questions, don't hesitate to ask them by Pronote or webmail. The idea is that you really need to be confident with this first part, because in a second video that we'll look afterwards, we'll detail what's happening in this Z scheme. But we had to do all these recaps for you to understand why some reactions were possible and some were not. Okay, so last recap. The Z scheme is in the thylakoids, so remember that the Z scheme is embedded within the thylakoids. Okay, so to finish this video, a little song just to end on a positive note. So if you master all this, then the next video, well, as Bob Marley say, everything is going to be alright. Okay, well, that will be all for this video. Goodbye and see you for the next one.